Imagine a world where forgetting is a choice, not a fate. What if we could augment our brains with technology? This is the promise of a memory chip, a device seamlessly integrated with our minds. Imagine instantly recalling vast knowledge or reliving cherished memories with perfect clarity. This future, once confined to science fiction, might be closer than we think. Scientists are exploring ways to enhance human memory using brain-computer interfaces. These devices could revolutionize how we learn, remember, and interact with the world. While still in their early stages, the potential benefits and challenges are enormous, pushing the boundaries of neuroscience and raising profound questions about what it means to be human. This exploration into the brain's complexities is not about achieving superhuman intelligence. It's about helping those with memory impairments and unlocking the full potential of the human mind. The journey begins with understanding the intricate workings of the brain, the ultimate frontier of science.
The memory chip, designed for biocompatibility, would be minuscule, smaller than a grain of rice. It would be constructed from biocompatible materials, ensuring the body doesn't reject it. This tiny device would house a network of microelectrodes and a miniature processor, all powered wirelessly. The microelectrodes are crucial. They act as the bridge between the chip and our neurons, the brain's communication cells. These electrodes, incredibly thin and flexible, would be able to detect and transmit electrical signals. This two-way communication is the key to the chip's functionality. The chip's processor would be designed for energy efficiency, minimizing heat generation within the brain. This processor would analyze, store, and retrieve information, acting as an extension of the brain's natural memory centers. The goal is to create a seamless integration between technology and biology.
Implanting the memory chip would require a minimally invasive neurosurgical procedure. Surgeons would use advanced imaging techniques like fMRI and real-time neural monitoring. This precision ensures the chip is placed in the brain region responsible for memory formation, the hippocampus. The surgery would begin with a small incision in the scalp, followed by a tiny burr hole in the skull. Using a specialized robotic arm, surgeons would gently guide the chip through the brain tissue, minimizing damage to surrounding areas. The chip's flexible design would allow it to conform to the brain's contours, ensuring a secure fit. Post-surgery, patients would undergo a period of observation and recovery. This time allows the brain to adapt to the presence of the chip and for any initial inflammation to subside. The success of the procedure hinges on minimizing risk and ensuring the patient's well-being.
Section 4. Bridging the gap chip and neuron interaction. Once implanted, the chip's microelectrodes come into play. They would be strategically positioned to interact with neurons in the hippocampus. These electrodes are designed to detect the faint electrical signals that neurons use to communicate. The chip doesn't control our thoughts or actions. It acts as a memory aid. When we form new memories, the chip records the neural activity patterns associated with those experiences. It then translates these patterns into digital code, storing them within its internal memory bank. Retrieval of these stored memories is equally remarkable. When we try to recall something, the chip stimulates specific neuron groups with the corresponding electrical patterns. This stimulation evokes the stored memory, making it feel as real as the original experience.
Section 5. Learning to remember. Calibration and memory access. After the surgery, a crucial phase begins: calibration. This process involves training the chip to recognize and interpret the user's unique neural patterns. Users would engage in memory exercises and tasks, allowing the chip to learn their individual brain activity signatures. Over time, the chip would become increasingly adept at storing and retrieving memories. Users could access their enhanced memory banks through a secure, personalized interface. This interface could be as simple as a smartphone app, allowing users to browse, search, and even share their stored memories. The chip's ability to enhance memory could have profound implications for education, personal development, and even creative pursuits. Imagine instantly learning new languages, mastering complex skills, or never forgetting a single detail.
The possibilities are as vast as the human mind itself.